barrier function design with convex optimization. So I personally prefer to think about the problem from a really control perspective, where we care about formal verification and formal guarantees, right? So in this talk, I will tell you how can we really design barrier function with guarantees. Yeah, great. So before the talk, I want to acknowledge these people. The first two, Antonis and Kostas, they were my PhD supervisor. And a large amount of this work are in collaboration with Claudio de Persis from University of Groningen, and also with Paul and from Oxford and Marta, who used to be a PhD student at ETH. Yeah, just Victor has introduced the background for barrier function, but so I still want to very briefly introduce it, just to synchronize our knowledge. So I will use one slide to introduce the concept. So we consider a continuous time dynamical system, which is described by a vector field x dot is f of x and u, where we say we have a set of initial states, denoted by calligraphic I over here, and we have a set of safe states, which is by this calligraphic S over here. So by control barrier functions, we mean we have a scalar function defined on the state space, which is a projection from the Rn to R over here, and we assume it's a differentiable function. So it should satisfy certain properties. For the first one, we say we should satisfy the set including condition for the initial state. By this, we mean the set of initial state should be a subset of the zero superlevel set of the barrier function, which is denoted by the calligraphic B over here. And we should also satisfy a set of including condition for the safe state, where we mean the set of calligraphic B should be a subset of calligraphic S, which is also denoted by the zero superlevel set of a function S over here. And we also call this S of X as a safety function, in contrast to the barrier function we are discussing in this talk. We have two critical functions. One is B of X, which is the barrier function, and one is S of X, which is a safety function. Describe the safety specification you have. And for the last condition, we satisfy the control invariance, which is basically just like on the boundary of the invariant set, the B dot should be greater or equal to 0. We should be familiar with it. So here we have a very simple example where we have a dynamical system. It's an autonomous system, non-linear system, polynomial system. And we have a set of initial state, which is this green set, this green disk over here. And we have this invariant set we designed, which is in yellow for this case. And this black set denotes the set of unsafe states, which is the complementary set of the safe set. It's an obstacle over here, basically. And we can see here for this case, we have the green set. The initial set is a subset of the invariant set, right? And the invariant set is actually exclude the obstacle, which is the black set over here. And also, we can observe that on the boundary, it's maybe a little bit small, but all these red arrows represent the vector field for the autonomous system. And we can see here on the boundary of the invariant set, which is denoted by this partial B over here, we can see here all these vector fields, these small arrows, actually point inwards this yellow set. They point inwards the invariant set. And the other condition, set including condition, hold in this figure. So we can conclude the safety, where we mean all the trajectories starting from this set I will never enter the unsafe set S over here, S of C over here. So we can conclude safety for this case. So the key question we want to ask is, are safety functions always control barrier functions? And if you've ever seen any robotics paper or maybe aerospace paper before, you might observe that many people simply they just use the safety function as the control barrier function, right? And they feed all these functions into control design problem. Or sometimes they have this relative degree issue, so they call the so-called exponential barrier function or high order barrier function or whatever barrier function technique. And they basically say we do this backstepping and we have a valid barrier function and we can design controller. Can we really trust all these functions? So in set language, we are asking, are safe set always forward invariant for autonomous system? And for control systems, we are asking, are these sets always control invariant? Well, for autonomous system, the answer is clearly no. We say the vector field points inwards the unsafe set on the boundary for many cases. So the safe set is not forward invariant. We go back to the previous case where I zoomed in the figure. So we can see here is the obstacle, this black disk over here, right? And we can clearly see that on the boundary of the obstacle, the vector field actually pointing inwards, right? it clearly say, okay, the vector field are the safe set are not forward invariant because you may possibly enter the unsafe set on its boundary. So it's clearly not forward invariant for autonomous system, which means that for autonomous system, you can now say, okay, the safety function actually tell you are safe. It means nothing. But how about the control system? I would argue that the question is very unclear because many existing work, they simply use the safety function S of x as a barrier function for safe control design. For example, they use this S of x function into a classical CBF code programming framework, where we basically say the constraint is simply the S dot plus alpha S greater or equal to 0. I design the controller, and hopefully it works. If it's not, we adapted this alpha function, and if it still doesn't work, I have nothing to do. Well, so from the optimization point of view, we are arguing whether the above optimization problem is feasible or not on every x. I would argue that they might be infeasible on some state x, even for the simplest case, the simplest linear system plus quadratic barrier function. I will give you an example to show safety functions are not barrier functions, where I will show you the vector field are actually very pathologic. So this is a very simple case, right? We have this linear system, and you can easily tell it's a controllable linear system. And here we have a specification of the safe set, which is outside of a disk. The disk is by x1 squared plus x2 squared greater or equal to 1. Very simple. Well, so if we just simply use this S of x as a barrier function for control design for the linear system, what will happen? Well, we can design this code programming framework, right? Here I pick this alpha to be 10, but it actually doesn't matter. You can pick like 100 or 1,000 or 0.1, doesn't really matter. So if we formulate this code programming for controller design, and we know it's a code programming with only one linear inequality constraint, right? So we can know the explicit solution for this code programming, which is piecewise by considering the activeness or inactiveness of this constraint. And if you look at the expression, you will see we might be in trouble if x1 plus x2 is 0, and also if x1 squared plus x2 squared is 1, which means that if you are on the boundary of the obstacle and the denominator of the expression is 0, you might be in trouble. So here is a visualization of the value of controller over here. And this black disk means the boundary of the obstacle for this case. And this figure shows the value of the u over here, which is a scalar because it's a single input system. And on the blue region, we mean the value of controller is nearly to 0. And on the orange region, the value is really large. And you can clearly see here, right, on the boundary over this region, the value of controller, it actually blows up, actually to infinity. But just for visualization, we cut the value to 100, but it actually blows up to infinity. And you can see here what will happen if you simply use this safety function as a barrier function. If you start from some region over here and you try to go around the obstacle, you actually need an infinite controllability to help make you safe, which means that the vector field is really pathological. It's really unsmooth on the boundary of the obstacle. So there's no way you use this controller in practice, right? And on the second case, we consider a mixed relative degree case, where still we have a very simple linear system where we have 3 states, x1, x2, and x3 over here. And you can see here, there is no control input over x1, but there are control input over x2 and x3. And x2 and 3 are feedback over this x1 over here. And we have a safe set, which is still x1 squared plus x2 squared. Am I clicking something? Maybe on the microphone. Yeah, it's still only over x1 and x2 over here. It's the same specification as the last case. What will happen if we use S of x as a control barrier function for this system? Well, similarly, we consider the relative degree. We consider the derivative of S of x with respect to the system dynamics. Very simple. We have the expression for S dot over here. And you can see here, because S of x is a function only over x1 and x2, right? You calculate the first order derivative, u1 will appear, but u2 will not appear over here for this case. So we have the expression. Well, it's really bad because only u1 appear, so it doesn't really matter how do you determine u2 in practice. And also, we can see here from the expression, when x2 is 0, x1 is 1, you are on the boundary of the obstacle, right? But if x3 is smaller to 0, then you have then you have this s dot is smaller to 0, which means that you are on the boundary of the obstacle. No matter how large is u1 or u2, you are always unsafe. So there is no way to design u1 and u2 to make you safe on this point for this system. You might ask, can we apply this exponential barrier function or higher order barrier function technique for this system? Sadly, the answer is no, because if you calculate the derivative over s dot again, you will have some cross product between u1 and you have a u1 dot over here, which means that you really need to design an integral controller for the system. Otherwise, there's nothing you can do unless you can apply this backstepping method. So we are arguing that the design barrier function are necessary for safety, even for the simplest case you can imagine. For linear system plus a disk obstacle, you still need to design barrier function. It's not universal to use safety function as a barrier function. How can we do this? So let's start from the simplest case still. We start from linear system. So we consider the following linear continuous time system, where it's very simple. We have no noise over here. It's basically x dot is ax plus bu over here. And we denote that we have a multi-input, multi-output system. We have x denotes the state, and u denotes the control input. And we consider we have a safe set specified as the zero super level set of s of x. And the question we want to answer is, how can we co-design the controller u of x and the barrier function that guarantee forward invariance for the set, and also the set inclusion where B should be a subset of S. That's the goal we want to do. So here we have the formalized CBF design problem for linear system. We are given this function S of X that specifies the safe set. The goal is to design a continuously differentiable function B of X, which is the barrier function, and also a locally Lipschitz continuous controller U of X, such that we have the set inclusion condition hold, and also the control invariance condition hold, where on the boundary we have V dot is greater or equal to 0. And I want to highlight here we need local Lipschitz, the controller to be local Lipschitz, because we always want the solution of the ODE to be unique for this case. So that's the question we want to answer. So you might think about it's a linear system, so this question might be very easy because, for example, for the Lyapunov function, we know for the linear system, we can design Lyapunov function with nothing, right? We just solve LQR problem, or we just solve the control Lyapunov function semi-definite program. We can just design Lyapunov function with 1 millisecond. Is it the same for barrier function? The answer is no. So Professor Andrew Clark has shown that even for verifying barrier function, I gave you a barrier function. I want to verify if that's a barrier function for a linear system or not. It's an NP-hard problem in practice. It's actually very hard. So the goal today in my work is we want to efficiently design barrier function with convex parameterization, convex optimization by some proper parameterization of the barrier function and the controller for this case. So we begin with the safe set specification. First, we consider the shape of the safe set. So on the first step, we split the state space into a direct sum of two subspace, which is denoted by R n overline and n underline over here. The reason why we split the state space is from the relative degree observation. We observe that for many applications, right, the safety function are always defined over only a subspace of the original system. For example, you have a car controlled by the acceleration. We always only say the safe set is defined over the position, not only the velocity, right? And for this case, the state space is naturally divided into the position space and the velocity space. And that's the meaning of this R overline and R underline over here. So the safe set, we consider the safe set, the zero super level set of this S of X. We consider the simplest case, where the safety function is a quadratic function over part of the state, X overline over here. Go back to the acceleration car case. This X overline will mean the position of the car. And the velocity, which is X underline, will not appear in the safety function. It's very natural. And we have the center, which is this C overline over here. It defines actually where the obstacle is on the state space, right? Yeah, and by assumption, we assume this S is positive definite and symmetric. It is natural, as by this definition, we actually assume the unsafe set is bounded on R overline, which means that you have a bounded obstacle on the state space you define. Well, you might ask, is this a really conservative setting? Because we consider the really simple case where we have a quadratic safety function, which is not really commonly seen in practice, right? What will happen if you have a polytopic obstacle? Well, we argue that the analysis would work on slightly change and lead to a more complex convex program if S is a semi-algebraic set. By semi-algebraic set, we mean this S function is a polynomial over here. So by polytope, this S function will be just some linear function, right? And you can define more complex shape of obstacles by using polynomials. I will not go into polynomial because it really makes the math in a mess. So I will just stick to this practical case in my presentation. And if you're interested, you can check my paper. We have more general settings. For example, if your obstacle is star-shaped, this is a star-shaped obstacle. Or if your obstacle is a smile face over here, where the blue regions are obstacle, this orange, their eyes and their mouth could be safe. And for this case, I don't know, it's maybe a kidney shape over here. All these shapes would work if they can be described by polynomials. Great. So we can go into this barrier function parameterization for my case. So let's go back to the barrier function design problem, where I recall the problem again. So we want to design this barrier function, where we need to satisfy these two conditions, right? Because it's motivated by Lyapunov function design. For Lyapunov function, we know if the Lyapunov function is quadratic, then we can design it using one single convex program. Can we do the same for barrier function? I argue that the answer is yes. By looking for a barrier function, which is a quadratic function over X, where the X is a full state space over here, we always want to design barrier function over all the state to get rid of this high relative degree issue. And the design parameter is very simple. It's just this omega matrix over here. So this omega, we want to design a non-singular omega such that this B would satisfy these above conditions. And similarly, this C represents the center of the obstacle, but now it's on the whole state space, not only on the obstacle, on the subspace that you define the obstacle over here. And because different from Lyapunov function, now we are actually considering design a quadratic function centers not on the origin, but on this point C over here, which means that we need to have a transformation of coordinate. We need to change the origin of the coordinate for the design, right? So the condition we want to satisfy for the change of coordination would be very standard. We need to satisfy a rank condition for the center of the obstacle, which is C over here, and the state and the input matrices over here, just to ensure there exists such a C and a change of on a forward, and a feed-forward control input case that satisfy the change of coordinate condition, which is basically AC plus BD is 0, which means that you can have a feed-forward term that allows you to change the coordinate. So we have two conditions that we need to satisfy. The first one would be a set including condition, which basically say the B should be a subset of S. And the second condition we argue is the forward invariance. So let's look at how can we ensure the first condition by convex optimization. So for the first condition, that's the specification for the barrier function for the control invariant set B over here, which is parameterized by this omega, a design parameter, right? And the S, which is defined by this quadratic safety function over here. So, and we say S is given, and we want to design this omega for this case. So we say if omega satisfies this condition, for the first condition, we consider the omega to be block diagonal over two metrics, omega overline and omega underline. They are both symmetric metrics. And if this condition holds, where S is a given matrix for the safety function over here, omega overline is something you need to design. If omega satisfies these conditions, we can argue that the B is a subset of this S over here. So in geometry, it's actually very obvious because you can imagine the safety function is a function of X overline, right? All we need is something like the projection of B onto the subspace should cover this very small set, obstacle set. For example, this is the obstacle set on the subspace X overline, Rx overline over here. And all we need to do is that the projection of the control invariant set should be the outer ellipsoid for this case. Then we can argue that if we go back to the original space, it would be a subset, which is basically this is the subspace for the obstacle, right? And this red set is the control invariant set, the projection. and we expand it into the original space, the Rn space, state space. The obstacle will be a cylinder for this case, because you actually expand from an ellipsoid to a higher dimensional space. It will be a cylinder. And the function we design is, you can see here, the first block is positive definite, and the next block is negative definite. So it would be a hyperbolic over here, which is basically cover the obstacle on the state space. So for the second condition, so you can see here, the first condition is actually convex, because we only have all these semi-definite constraints over here. So it's a convex constraint in general. And for the second condition, we want to make sure the set B is forward invariant. And you can immediately see it's very similar to the Lyapunov function. The only difference is, like, for the Lyapunov function, omega is positive definite, right? And for our condition, we only have the omega to be full rank. It's already enough for to have a convex condition over here. So for this condition, we want to make sure on the boundary of the invariant set, we really satisfy the B dot is greater or equal to 0. So we can use the standard Barrel function trick to reformulate the condition, where we introduce this parameter alpha, which is a positive constant over here, and we say B dot is greater or equal to minus alpha times B. Very standard CBF QP type of condition we have. And recall that we have a quadratic Barrel function. Now it's enough to consider linear controller. Just for linear system, we have a linear controller. It's an affine controller, because we have this non-zero deviation term D over here, which is to compensate the center of the obstacle. And because we already have this AC plus BD is 0 condition, now we can say the closed loop system is actually in feedback form with a coordinate centered on C over here. And then we can reformulate the forward invariance condition, which is basically the derivative of this quadratic function should be greater or equal to 0 over here, which is basically something like this. The only difference between this condition and the Lyapunov function condition is we have a non-zero C over here, and omega is only full rank, not PD. And you can see here, if you want this condition to hold, because it's already block diagonal, so it's very simple. You only need to separately consider these two blocks over here, which is basically you need alpha should be 0 for this case. This is very different to general Barrel function, where always you have a positive alpha. For linear system, you only need alpha to be 0. That's enough. Because you have a minus alpha over here, and you want to argue the whole thing to be greater or equal to 0. So the only choice of alpha would be alpha is 0 for this case. So this is very good, because you can see here, actually for the first condition, you have a multiplicative term, which is alpha times this omega inverse, right? If you want to co-design alpha and omega, you end up with a bilinear condition. But now we have alpha should be sufficiently and necessary to be 0, so this term will be eliminated. So the only condition is very simple. It's just like the reverse direction to Lyapunov function condition, which is basically by the standard change of variable trick, and we use short complement. There's no short complement for this case. So we can convexify this condition very simply with A omega plus BY plus the transpose should be greater or equal to 0 for this case, where the control input K has been encoded in this Y variable over here, just like the Lyapunov function. So, and also we can maximize the size of the invariant set. And here you can imagine, because the obstacle is ellipsoid on the subspace, right? So to maximize the volume of the invariant set, we can just minimize the size of the projection of the invariant set, which is basically you minimize the volume of the ellipsoid defined by the Barrel function over here. The way we are doing this is, instead of doing this log determinant, we are actually minimizing the trace just for convexity, because this minus log determinant is not really, it's actually concave for this case. So we end up with using this linear function over here for the problem. So now is everything. It's the math part for this Barrel function design for linear system. It's very simple, right? I mean, if you understand the Lyapunov function, you understand the counterpart for Barrel function. So you might ask the question, is this useful, right? If I have a really complex system in practice, can we actually use all these techniques for linear system, design Barrel function, and design safe controller? I mean, it looks really conservative, but it works really well. So in summary, the formulation for Barrel function design would be, we consider this linear system and the safe set. And all we need to do is something like we pick the center of the obstacle, where the C bar is given by the safety function over here. And you need to pick this C underline over here, just as a design parameter or as your choice. you want. And then we solve this very simple semi-definite program. And that's it. You have a barrier function, which is a valid barrier function for linear system over here. And we can argue that with this controller, y omega inverse, which is the standard parameterization, we have this set B to be forward invariant for the system. And it satisfies this set inclusion condition. Before diving into a more practical case, I want to give you a very simple case to show how can we apply this method. So we consider a point mass vehicle on a line over here, which is very simple. We have two states, a position and a velocity, where for this case, this x over line represents the position and this x underline represents the velocity over here. So the safe set for this case is simply defined by you have an obstacle on the position space where you argue that the position should be greater to 1 or less than -1 over here. You should never crush to this cylinder centered on the origin of the position space. So for this case, you can simply say S matrix X will be 1, and C bar will be 0, which is just like the center of the unsafe set over here. And the CBF and the controller would be parameterized by the design parameter is x overline and x underline, which are just the scalar for this case. So you have a quadratic barrier function where omega overline is positive and this omega underline is negative, and you have a linear controller over here. The forward invariance condition is actually look like this. And now it's basically very simple. It's a two-dimensional semi-definite constraint. And actually, you can reformulate it. You can reformulate the forward invariance condition as very simple scalar conditions over here for this case. And similarly, the set inclusion condition, it basically says, okay, similarly, there should be a subset of the safe set, and it's a semi-definite constraint. And with the standard reformulation, you can change it into a scalar constraint, scalar inequality constraint, by using Schur complement over the first block, 1 over here. And we can design the control invariant set, which is basically the hyperbola over here. The green set is the obstacle, where we say the x overline is the position, and the x underline is the velocity over here. So the obstacle will be a cylinder on the state space over here, expanded from the segment lie on -1, 0, and 1, 0 for this case, right? It's a cylinder. And the hyperbola is a invariant set over here. And it's very reasonable, as you can imagine, if you have something like you are on the position, which is positive, and you have a negative velocity, you are going to crush the obstacle over here. And all you need to do is something like you need to design a controller that drags you back, right? Something like this. So yeah, for this simple case, you just solve a linear program and you're done. It's a barrier function. And now we can have a look at more practical example, and it's way more complex than the previous one. We have a robotic manipulator over here, and the goal is to avoid all these boards and grab the something behind this. And you can see here we have a camera on the robotic manipulator, and it helps you to detect the environment. And what we are doing something over here is something like we are designing this barrier function online based on the sensing of the environment. We can be solving this linear semi-definite program and efficiently design the quadratic barrier function based on your local detection of the environment. You can see here with the robotic arm is moving, it actually detects a different surface of the obstacle, which means that you really need to design this barrier function based on the current detection of the obstacle. So we have an online algorithm for this, and we have a paper for this work. And it's actually highly efficient because for this robotic manipulator, the dynamics are actually nearly linear on the operation point, right? And you can see here, all these obstacles are actually bounded. So based on your local detection, you can efficiently design barrier function, which helps you to ensure safety for this case. Well, a lot of extensions are possible for this work, where if you are interested, you can check out the paper. So for the first extension, now in the presentation, I just show you if the safe set is defined by a convex and a quadratic function, right? And it can be generalized to any semi-algebraic set, as we have shown before, like the star shape or small face shape obstacle. They are all possible, but through a more complex convex optimization framework. And also, for the case where the safe set is bounded, this is very commonly seen for power system, where you're trying to say something like, I want my current or voltage to be within a certain threshold. Then the safe set will be bounded. I can still design the barrier function, but it's just like the level set of the Lyapunov function for this case. And for this case, you can imagine we have a bounded initial set, and we have an obstacle over here, we have a safe set over here, which is nearly bounded, and then we can design a bounded control invariant set over here for this case. Yeah, and a very simple case, we have an obstacle, which is still a bounded obstacle, but it's very similar to the previous one. And we have an initial set, which is in this black level. So we can design this ellipsoidal type of invariant set over here, where you can see here all the trajectory started from the initial set will remain in the safe set for this case. And there's a very interesting example where for most cases, people argue that we can just design a Lyapunov function, right? And we pick the maximal level set as the invariant set for this case. Would that work? The answer is no. For this case, we have an initial set, which is this rectangular over here in gray. And we have a safe set, which is basically this orange set, this is the purple set over here. Because if you want to design a Lyapunov function and use a level set to include the initial set and exclude the unsafe set, it is impossible because the shape can be really bad. For example, you use the LQR type of Lyapunov function. This is the level set for the Lyapunov function in blue. And you can see here, if you slightly enlarge, it will actually crush the initial set and the unsafe set. So there's no way to find a level set of Lyapunov function as a barrier function for this case. But by solving this semi-definite program, you can actually find the barrier function, a feasible barrier function over here. Yeah, and also we can include this polytopic two-norm or infinity norm constraint over input to this program to design barrier function for a system with limited control authority. Let's go into a more complex part where we consider barrier function design for nonlinear system over here. The idea are very similar, but just the optimization landscape slightly change. Now we consider a continuous time control affine nonlinear system over here, where x dot is fx plus gxu, commonly seen in almost all barrier function-based papers. And we assume we have this control input limitation set over here, which is calligraphic u over here. And similarly, we have a safe set defined by the safety function s, and an initial set defined by initial function w over here. The goal is similar. We want to design this b of x such that the initial set is a subset of the control invariant set. The control invariant set is a subset of the safe set, and also we need to have this control invariance condition hold, right? By interpreting into algebraic condition, it actually means for the first condition, your b of x should be greater than or equal to 0 for any x such that wx is greater than or equal to 0. If you are in the initial set, wx is non-negative, right? So the barrier function will also need to be non-negative for this case. Similarly, we have interpretation for safety, and we have interpretation for control invariance, which are basically algebraic conditions over all these functions. However, the problem is really complex because you can see here, if you want to design a barrier function, we always need to co-design barrier function and controller for control systems, which means that you will have this multiplicative coupling over here. You have b multiplies u over here. The second challenge is that all these conditions should hold for any x within a set, which means that if the measure of w, if the measure of initial set I and safe set s are not 0, you will have an infinitely many constraints for all these conditions. It's really challenging. So the way we are dealing with all these difficulty are actually from primary school math, which is called sum of square relaxation. So the problem of interest of our problem is that we want to ensure positivity of functions over some sets. So basically, we are arguing whether all these barrier functions are non-negative over the initial set, or is it negative over the unsafe set? That's the problem we are arguing. So the key technology is called SOS, which basically we say we have a multivariate polynomial f of x. It's called a sum of squares polynomial termed by SOS if it could be written into a sum of squares of polynomials. Very simple, right? So basically you see if this f can be written in this form, it's always non-negative, clearly, because every fi square would be non-negative. You sum it, it's always non-negative for this case. So there's a very simple lemma called SOS polynomials are non-negative, straightforwardly. But the reverse way is not true. So there exists some non-negative polynomial which are not SOS polynomial, as we know. So, and also, if I give you a polynomial, how can you check if that's a SOS polynomial or not? This can be done with very simple semi-definite program, where you say, I give you a polynomial. If it could be written in this form, v of x, which is a vector, transpose times a q, which is a positive semi-definite matrix, and z of x. You can see here if this Q is positive semi-definite, and it's just in the squared form. So clearly, this f is non-negative. So if f can be written in this form, it's an SOS polynomial, which means that it is non-negative. So checking a polynomial is a SOS polynomial can be done in polynomial time. It's very simple. Our problems are unfortunately slightly more complex. We're actually checking positivity of function over set. So basically, for example, for the barrier function problem, we're checking whether b of x is positive, is non-negative over the set, where the set is defined like this, right? And similarly for safe set, very similar, just in the reverse way. And also for the control invariance, we are all checking positivity of polynomials over some sets. And the assumption that everything is polynomial, f of x, g of x, s of x, and w of x are polynomial functions. We can actually interpret all these conditions using SOS constraint. I will only interpret one of them to you. So for the first condition, you look at here, we want b of x to be greater than or equal to 0 for any x belongs to the set, right? The way we are doing this is we are actually introduce a non-negative polynomial, sigma 1 over here, which is an SOS polynomial. And we say if b of x minus sigma 1 of x times w of x is SOS polynomial, then the first condition is true. How can we say this? You can imagine, look at the first condition. If w of x is greater to 0, and s sigma 1 is also greater to 0 because they are all SOS. And if b of x minus something non-negative is also non-negative, then we say b of x is non-negative, right? Very, very straightforward. If w of x is greater to 0, then b of x is greater or equal to 0. So we have a SOS condition that is sufficient for the first set inclusion condition. And you can imagine this sigma 1 are some decision variable to our program. And this whole thing is something like you are arguing whether a polynomial is a SOS polynomial or not. And this is a semi-definite constraint, which can be done using the last lemma. And similarly, we can interpret the initial set, we can interpret other conditions like the safe set inclusion condition and the control invariance condition, all of them using SOS constraint by introducing proper polynomials over here. And they are all SOS polynomial. So here we have our lemma. So we under the above assumption, where we assume everything is polynomial functions, and let b of x and u of x, the controller, and the barrier function to be polynomial functions that we want to design. Then if we want lambda 1 of x is a polynomial, and we have this condition hold, we satisfy the control invariance condition. And now we have SOS conditions for set inclusion and control invariance. They are all SOS conditions, which can be transformed into semi-definite programming over here. Yeah. So in conclusion, we can have a SOS program, sum of squares program for barrier function design, where we are solving the following program such that we are going to design b, u, and some multiplier or some auxiliary variable in the design program. And similarly, we have this multiplicative coupling between b and u over here. So the heuristic we propose is something like, for the first program, we fix b, we solve for u, and for the second program, we fix u and solve for b, and do this iteratively. So for the first program, we fix this b function, solve for u over here, and we feed this into the second program where we fix u, solve for b, and we do this iteratively until it converge. It's a heuristic, so there is no convergence guarantees unless you have some warm starting for barrier function, but it really works in practice. As an example, we have this polynomial nonlinear system, and we have a series of control input constraint in an initial set and safe set for this case. And we can design the invariant set, which is in this gray set over here. And you can see here, it includes the initial set, and it is a subset of this disk safe set over here. And all the vector field point inwards on the boundary. So it really works. And on this figure, I show you the value of the controller. And you can see here inside the control invariant set, the control input is actually upper bounded by 1.5 for this case. So the time is up. So I will just conclude my work. So here is the QR code for my Google Scholar if you are interested in any of these papers. And as an extension, so all this work can be extended to discrete time system, but much more complex, using some rational polynomial technique. And also, we can do this sample-based SOS for CBF design, especially when you do not have the function that describes your safe set. For example, in practice, you don't really always have a function that describes the obstacle, right? So you can do this using a sample data way. And also we can do stochastic design using some really annoying stochastic analysis for bounded and unbounded process noise over here. And we can, and the last speaker argued this method only applies to polynomial system. I would argue no, and this is well known. So for non-polynomial system, there's two ways we can do. For the first way, we can do Taylor expansion straightforwardly. And a more mature way is we can recast non-polynomial system into polynomial system plus equality constraint. This is accurate, sufficient, and necessary for any elementary function. For example, triangular functions or these exponential functions, they can all be recast into polynomials. And for this presentation, here are a series of reference by me. And I have this tutorial paper, which is a chapter on a book. And if you are interested in this field, you can check this paper over here. So as a conclusion, so we propose convex optimization, SOS, and SDP-based method for barrier function design. And we have convex formulation for a linear system. We only need to solve one single SDP to co-design quadratic, a non-convex, CBF, and an ifine controller over here. And the method is highly efficient. And I will say that it is guaranteed, in contrast to 99% learning-based method that do not incorporate any form of verification. Let's see, neural network verification. And I would argue that neural network verification skills much worse than SOS-based method for any neural network architecture. So first direction, we are interested in exploring sparsity for SOS program for acceleration. And also we are interested in data-driven design without models, or let's say accurate models. Especially we are interested in this Markov decision process model for reinforcement learning. And another way would be time-varying barrier function design, because there are a lot of work on time-varying diagonal function design. They are all straightforwardly extendable to barrier functions, and a lot more. So time is up, 43 minutes. I hope it's good. So thank you very much. And here is my email address. I'm afraid I have a 1 over here because there are so many Han Wang at ETH. So that's my email address. If you have a question, message me. Don't forget to have this 1 email address. Thank you. Yeah, I'm the number 1. Yes.
Just a very one simple question.
Yeah.
That's like you are learning the constraint variance set by semi.
Yeah.
And this is a sufficient parameter, which means the set requirement is different from the true maximum.
Sure, yeah.
Do you have any way you can quantify that?
Sure, yeah. That's a very nice question. I would go back to the previous case, the linear system case, sorry. How can I go back? Yes, we're here. This case, for example, this case. So if you look at the maximal reachable set by solving the reachability problem, the maximal invariant set for this case would be you need to fill this part into yellow and fill this part into yellow as well, because very straightforwardly, if your position is positive, your velocity is positive, there's nothing you need to do, right? So this will be yellow. So the way we can do this is we can consider a union of invariant set over here, where we consider a union of this one and a union of some other quadratic barrier function, which are filled in, certified all these rectangular on the state space. The reason why we have this gap is because you can see here, we have no cross term over this omega. We assume this omega to be block diagonal, right? That's all we need to do because we need to have this non-singular condition hold in practice. So in practice, what we can do to fill this gap would be we consider the off-diagonal term over here and consider the union. That's it. Yeah, but still, we have no converse theorem for this case, unless you are doing this bounded design by diagonal function. Yeah, thank you. Please.
Great. I was wondering, how would you consider input?
Yeah, thank you. It's a very nice question. So the way we formulate the input constraint for this case is something like, because the invariant set is certified by a quadratic function, right? And you can imagine if you have if you have input constraint like this 2 norm or infinite norm constraint over your input, it will become a quadratic constraint again. And you use short complement, you are actually convexify all these conditions into semi-identity program. So it's very similar. So basically, you are saying something like inside the invariant set, your input is bounded. So we can discuss later, please. Yeah. Yeah, that's the next question. So we actually, it's very much for this application, we don't really consider some episodic scheme for the framework. We just consider the computational cost for solving this SCP. And for this case, it's very simple. It's a linear system, and we sample some data from the obstacle. So it's basically just the SDP with a really low dimension. So we solve it up to like, I don't remember, but it's very much like slower than the control frequency for the manipulator, but still as fast as possible. And in practice, I would say, I don't have a good idea in mind. I think it's very much depends on, you can design some heuristic scheme, depends on how different your obstacle looks like at this moment, or maybe there are some smarter way. Yeah, thank you. Thank you. Yeah, please.
One last question.
Yeah, please.
For the robotics.
Yeah.
Where you have
yeah.
When you say you're using visual information, right?
Yeah. Yeah.
So since where's the camera placed? Is it on top of the robot?
Yeah.
Right?
Yeah.
So by that, the camera moves with the robot, right?
Yeah.
And therefore, you have just partial knowledge of the environment.
Yeah.
Basically, your assumption at one time step is maybe not correct anymore in the future time.
Yeah.
Right? With that, the safety guarantees are somehow like weakening.
Yeah.
Find a way to address this problem.
Sure. Yeah. For this case, I think all you need to do is something like, because we are actually controlling the end effector of this robotic arm, right? And the camera are actually placed very close to the end effector over here for this case. And because obstacle, actually, we store the point that's on the boundary of the obstacle, and there's a historical data set for the boundary point of the obstacle, right? And you can imagine if you have all this historical data, and all you need to do for the following semi-definite program is something like you just take care of all these obstacle points in a semi-definite program. But the cost is something like you are growing the dimension of the SDP with time.